Hello guys, welcome to the PLC Goods online video tutorials. My name is Syed Reza. I am one of the educator and the site admin of plcgoods.com. Now in this video we are going to learn about introduction to PLC. We are using the PLC name Siemens S7-1200 and TIA Portal software. Well, what's the goal of this tutorial? See this pyramid, which is called the Industrial Automation Pyramid. At the lowest level, you can see there are a lot of electrical instruments such as push buttons, thermocouples, transmitters, sensors, and micro switches, which can tell us what output it is as motors or signal lamps that should be turned on or off. But we cannot check all these devices simultaneously. Today's PLCs are often used to accomplish this task. PLC is the short form of programmable logic controller. These devices help us to have automatic control in industries. Besides PLC, some displays visualize industrial processes for us, which are called human-machine interface or HMI. Maybe there is more than one PLC or HMI which can exchange data with each other over a suitable industrial network. The goal of these video tutorials is to learn how to program a PLC and its HMI to control and monitor an industrial process as a supervisor. It is also to collect your industrial process data to help with your management of the process. In this lesson, after the introduction part which has been discussed, we are going to understand PLC hardware and its wiring. Then we will show you how a PLC executes a simple program. After that, we will show you some basic points of its memory that will be told, and finally we will have a summary of this tutorial. Before we get started with today's video, I just want to inform you about all the great content I have been releasing on the PLC Goods YouTube channel, which includes topics related to industrial automation, PLC programming, HMI and microcontroller-based developments and projects. My name is Syed Reza Fattahzadeh, and if you enjoy this video, I would appreciate it if you could click the subscribe button as well as the notification bell to receive the latest and greatest content I will be posting through the channel. Please be informed that by clicking on the join button and paying a small monthly fee for as long as you want to continue, you can become a channel member to get access to cool perks such as to have access to my exclusive videos, WhatsApp support number, and access to PLC control program codes existing in my YouTube channel. I will add more or edit these in the future and do my best to not to disappoint you and create these hard-hitting tutorials and content that you all like, but I am still growing and I am expanding the channel as well. At the end of the day, I still appreciate your support and consideration. These are my PLC and HMI that are provided by Siemens company, which will be used in this tutorial. Both of them can be programmed with the TIA Portal software. Even though many companies produce these types of devices, fortunately, most of them follow the IEC 1131 standard rules. So if you can work with a PLC or HMI, it makes you learn to work with others easily. The main part of these or any PLC station is its CPU. CPU is the written abbreviation of Central Processing Unit. Before starting the video, please pay attention. This tutorial of TIA Portal and S7-1200 has been prepared for the educational purposes. So, to work with these or similar devices, you also need to read related documents such as their catalogs. Alright, let's start with the CPU. In this course, we will use a CPU S7-1200 from Siemens company. The Simatic S7-1200 controllers can be classified into 5 categories. In this tutorial, the S7-1212C model will be used. As you can see, there are some terminals behind the top door cover. The first 2 terminals are connected to the external 24 VDC power supply. Some models need a 120 or 220 VAC. As you can see, these can be distinguished with the AC word in their model's name. So, you must take care of that, because if your PLC is a DC source and you use it with an AC source, it will burn out immediately. For safety, the next terminal should connect the PLC body to the earth. This CPU has a 24 VDC that supplies sensors or other instruments which may be connected to it. Next, we will have the digital inputs. A digital input has only 2 states, which are on or off. The first terminal is common for all other 8 digital inputs. These digital inputs work based on a 24 VDC. The last 3 terminals are used for 2 analog inputs. Analog sensors give us a signal such as 0 to 10 volt VDC or 4 to 20 milliamps. Finally, we need to use a memory card, which can either be a transfer card or a program card. We can use a transfer card to copy a program to the internal load memory of the CPU without using the software, and use a program card as an external load memory for the CPU. In front of the PLC, there are some LEDs. On the left side, you see 3 LEDs. The first LED shows whether the CPU is running or if it is on stop mode. The second LED determines if there is any error in the PLC configuration, and the last one is for maintenance requests. On the right side, these LEDs tell us which digital input is on or off. So we have some green lights here, which will indicate that the input is on. If there is no green light, it means all inputs are off. Here you can see my PLC model. After that, these LEDs show which digital output is active. As you can see, below the PLC, you can see the LAN connector. The CPU can connect to the Ethernet network over the LAN interface. For example, it has to be programmed or connected to an HMI. And these LEDs show the status of this connection. Here are the PLC outputs. This PLC has 6 digital outputs which are powered by a 24 VDC source. Some PLCs use relay outputs. These PLCs use the relay word in their model's name instead of DC. And finally, here is the article number of my CPU. The PLCs usually can be installed on a rail easily. Also, you can have other S7-1200 models besides the CPU with this connector. My CPU doesn't have any analog output, so I will need to connect an analog output module like this. If I need another module, it can be added with this connector again. Moving on to the left connector, which is used for communication modules. Also on this CPU, we can use either a signal, a battery, or a communication board. Now, let's see some points of PLC wiring. This is simple wiring of my CPU with this information. The wiring of this CPU and others are pretty much the same. But I recommend reading related catalogs for each device carefully. First, this CPU needs an external 24 VDC power supply to work. Please look carefully here. I will use the internal 24 volt DC to power the digital inputs. At the bottom of the CPU, with this LAN connector, the CPU can communicate with an HMI or computer, and to power the digital outputs, we can use an internal 24 VDC too. This wiring is for syncing inputs. Right here, pay close attention. In the syncing wiring, when this switch is pressed, a 24 VDC can reach the PLC input, but when it comes to sourcing type, 0 volt appears on the PLC inputs. The reason for this is the different type of sensors. PMP sensors use syncing wiring because these sensors provide generally 24 volts in the PLC inputs. On the other side, if we are using NPN sensors that give us 0 volts, then the sourcing wiring must be used. In this course, we will use the syncing type. Here is another point. PLC can turn an output which needs a low current, but what about a motor that needs 220 volt AC and high current? In these cases, we have to use a relay or a contactor. When PLC turns on this relay, its contact changes to close and it then turns the motor on this power circuit. We have seen my CPU parts and some points about its wiring in the previous video. In this video, we are going to know how a simple program is executed by the CPU, and then some points of its memory will be explained. This is probably the simplest wiring of my CPU with a single input and output. And also this is a simple PLC program. How does a PLC execute this program? To answer the question, suppose here is the virtual power line. So the power can reach this contact. The address of this contact refers to this PLC input. So when this switch is pressed, this 24 volt appears at the PLC input. Then the program, the CPU, makes this contact to be closed. Now the virtual power can reach this output. Similarly, this address refers to my first digital output. So the PLC activates its first output and thus makes the H1 lamp turned on. Now let's see a flowchart which shows an overview of how the user program is executed. There is an operating system and a user program. After the power supply has been switched on, the control processor checks the consistency of the hardware and parameterizes the modules. Then the startup program is executed once if it is present. User programs are usually divided into individual sections called blocks. OB or organization blocks represents the interface between the operating system and the user program. The operating system calls an OB for specific events. For example, OB100 is executed once when the operating mood of the PLC changes from stop to run. In each OB block, if the user program is long and complex, it can be written in some FC or function and FB, which is an abbreviation of function block. After the startup mode, in the run mode, the operating system first updates all PLC outputs and then reads its inputs. After that, PLC executes the main program, cycling until the PLC is turned to a stop. In each cycle, the operating system updates the outputs and inputs and calls OB1 as the main block. Every time an interrupt occurs, the operating system calls for the appropriate OB and then comes back to the main program. This red line is known as cycling in program execution. Alright, moving on. The CPU has three modes: a stop, a start up, and run. Let's see what the CPU does in each mode. In the stop mode, the CPU does not execute the user program. It handles any communication request and performs self-diagnostics. In this mode, the run stop LED will be off. As you can see, in the start up mode, the CPU does A to F tasks, which are: A. Clears the process image inputs. Process image inputs is a memory where PLC stores its input states. B. Initializes the process image output. As previously, process image outputs are a memory where PLC outputs states are stored. C. Processes the startup organization block, such as OB100. D. Copies the physical inputs to the process image input. E. Interrupts are queued to be processed in the run mode. And the last item, F, enables the physical outputs to be changed. In the startup mode, the run stop LED is flashing, indicating that the CPU is in a startup mode. Okay, now let's see run mode. In this mode, CPU first updates the physical outputs, then reads the physical inputs and updates its inputs image memory. After that, run the user program. This starts with OB1 as the main program block. Then the CPU performs some self-test diagnostics, and every time an interrupt occurs, The operating system calls appropriate OB and then comes back to main programs and also responds to communication requests. In this mode, the run stop LED will be green and the CPU executes all these tasks, cycling until the PLC is turned to a stop. Also, error and maint LEDs can help us to know the start of PLC. For example, flashing red in the error LED indicates an error, examples being an internal error in the CPU, an error with the memory card, or a configuration error. Moving forward, now we have seen how a program is executed by a PLC. On the other side, an industrial program needs to know electrical equipment status and signal values. So how does a PLC store this information on its memories? As you know, on a memory, a bit is the smallest unit of storage with two states which are 0 or false or 1 or true. A digital input of PLC only has two states, so it needs 1 bit. 0 when input is inactive and 1 when input is active. If we have 8 bits, it's called a byte. 1 byte can store 256 states. See this table. We can store 0 with 8 zeros, 1 with 7 zeros plus 1, and similarly 2, 3 to 255. There are a lot of standards to save data, such as numbers, time, and date, which will be told later. For example, let me use the 7th bit to store the sign, 0 for positive and 1 for negative numbers. So based on this table, I can store negative numbers too. These numbers can be electrical signal value or some industrial parameters such as motor speed or water level. If we need more precision, we can have 65,536 states with 2 bytes, which are called a word. Now let's see how we refer to a location on memory. A CPU has 3 important memories which are used frequently: input image memory, main memory, and output image memory. Let's start with main memory. We use the M letter for this memory. This table shows memory structure. The first column shows the byte number for each row. In the other words, for each byte, we have 8 bits, bit 0 to bit 7. For example, see this location of memory with its address as M0.6. M refers to the main memory. The next number determines the byte number, and after the dot, the second number determines the bit number. Similarly, you need to pay attention to these two addresses, M1.4 and M5.2. If we want to refer to the whole of a byte, we just need to write the byte numbers such as MB2 or MB5. If we need a word, W is inserted between M and the byte number, such as MW0, which consists of byte 0 and byte 1, or MW3, which refers to byte 3 and 4. Here you need to pay attention to MW4 and MW3 addresses. Byte 4 is used for both of them. So if MW3 is used to store a number, we should not use MW4 to store another number. The rules which were told are true for the input and output image memory. We just need to use I or Q instead of M. TIA stands for Total integrated automation. In this lesson, we will learn what the various features of the TIA are. We will then define a simple project. After that, in the portal view of TIA, we will create a project. Then in the project view, we will see how to configure and program our PLC and how to download or test the program. Finally, we will have a summary. The word TIA is short for Totally Integrated Automation. But what can we do with this software? Firstly, we can program some of Siemens company controllers and monitoring devices such as our controller and this basic panel. These are the basic devices in industrial automation. Also, we can set network connections of these two devices with the TIA. Because these two devices support LAN cables like this one, so these devices support the Ethernet network and we can make their connection with just a LAN cable and TIA software. Let's see the other features of the TIA software. Each industrial process has its special requirements. For PLC stations, many modules can be chosen and used according to the requirements. Also, we can program our drives using drive and motion integration plugins, which are in TIA software. We don't need any extra software for that. It may need to have some more secure access to a PLC or HMI by allocating some passwords, which the TIA software can do it for us. And lastly, there is a diagnostic. Various alarms and errors can be considered in the software or can be monitored. So, the TIA software is total integral automation that can be used to program both HMI and PLC using all these features. That's wonderful to do many things in automation industries just with a platform. Now let's define a simple project and then do it with our PLC and the TIA software. Here you can see an industrial circuit in EKTS, which is a software to simulate simple industrial circuits. At first, the power cannot pass through this normally open switch and contact. Thus, the K contactor will be off. This is the same way the three-phase motor will be off. If the start button is pressed, the electrical voltage reaches this contactor and then their contacts are closed. Then electrical power can reach the three-phase motor and turns it on. If I release the start button, the motor will stay on. Because of this contact, and if I press the stop button, the contactor and the motor will be stopped. Let's test it again. As you can see, industrial circuits usually have two parts, a power circuit and a control circuit. Power circuits are simple, but their voltage is high, 220 volts or higher. On the other side, the voltage of the control circuits is low, but usually there are a lot of sensors, switches, timers, etc., which make complexity in their wiring. Here, PLCs help us to understand their logic in a CPU with simple wiring. Now you can see another industrial circuit on the right side. The circuit has two control and power parts too. But looking at the circuits, a PLC is used in the control part. My PLC model is CPU 1212C DC/DC/DC with this article number of Siemens company as the first circuit. Here are two switches in PLC input and a contactor in PLC output with the same power circuit on the right side. Our project is to program this PLC to turn on the three-phase motor based on the left circuit logic. To do this project, I'm going to write this program on the CPU. Like the right control circuit, This program has a normally closed contact to stop, a normally open to start, and an output with its normally open contact. But how can we change the state of these contacts inside the CPU? Pay close attention to the PLC wiring and its program. The start contact with I0.0 address in our program will change to close. If the S1 switch is pressed and 24 volt DC reaches the PLC input with the I0.0 address. Similarly, the stop contact with the I0.2 address will change to open if the S2 switch is pressed and 24 volt DC reaches PLC input with the I0.2 address. Finally, when the program turns on its output with the Q0.0 address, PLC enables its Q0.0 output. Then the 24 volt DC can reach the K contactor, which turns the three-phase motor on. Let's start with the TIA software to do this project. TIA software has two layouts. It starts with the portal view. In the portal view, we can quickly decide what we want to do and call up a necessary tool. In other words, the portal view is more suitable to create or manage projects, but the project view is a structured view of all components of the project. Here you can program CPUs, configure hardware, etc. with their details. Let's get familiar with the portal view. This is the start menu, and below that here are 5 portals which depend on the products that have been installed. We should open, create or upgrade a project to activate these portals. Now let's click on create new project. Then write a name for the project, and after that write here your name as a programmer and then click here. Now let's see what these 5 portals are. In the Devices and Networks portal, we can configure the hardware of our PLC. Here we can select our hardware components, position them, and then set their properties. If several devices are networked, their connections can be defined here. The PLC Programming portal contains all required tools for generating the user program for PLC stations. In the Motion and Technology, other automation technologies such as motion or PID controllers can be inserted, configured, and used in the project. In the Visualization portal, we can generate the operator control and monitoring desktop for HMI station. Using the Online and Diagnostic portal, we can connect a programming device to a PLC, transfer and debug programs, and detect faults in the automation system. Now let's add and configure a PLC station. So you need to click here. As you can see, there aren't any devices. So click here to add a device. Here are the 3 types of devices. Select the controllers. The Siemens controllers which can be programmed are listed here. I am using a CPU 1200C DC/DC/DC which is in Simatic S7-1200 family. We can find it here. Well, here are 3 article numbers. My PLC article number is 6E S7-212-1AE40-0XB0. Also, you can select this item, unspecified PLC, then start programming, and after that get back and configure your hardware. If you don't have any controller, don't worry, you can select any type of CPU. This is because the programming rules of these controllers are similar, and you will be able to test your programs with a simulator in the TIA. Now click on Add. It will take a couple of seconds to add this configuration to your Siemens TIA. Well, after adding the CPU, TIA software will switch to Project View to configure the hardware in detail. If you want to come back to Portal View, then click here. In this video, we are going to complete the project which has been defined already. Let me switch to the Project View. The Project View shows all elements of the project in a structured form in various processing windows, which may change their contents. Now, because we have selected a CPU, related tools will be shown for PLC configuring. Let's get more familiar with Project View. Underneath the title bar, there is the main menu with all related commands. Commands are available for selection depending on the currently marked object. The menu commands which cannot be selected are displayed in gray. The same functionality is available with the shortcuts. These are always present in the project view. In the center of the project view, there is the working window. The contents of the working window depend on the editor currently being used. Now that the CPU is selected in the center, from the right list, we can choose modules that may be used beside the CPU. And you can see when a module is chosen, permissible places are shown with a blue rectangle. Like what I am doing, try to insert other modules and learn what they do using the internet. Let me delete the inserted module to have only one CPU. After the selection of an object in the blue window, in the Properties tab, we can change its setting. For example, the next step is we have to link this PLC to my computer. In that case, we have to check the IP addresses. Click on the LAN connector of the CPU. Here you will see an IP address which is 192.168.0.1. So this is my PLC IP address. This address can be changed, but you must make sure the PLCs or other devices should have a different address in a network. This is a basic concept of network. In this course, I will use one PLC, one laptop, also one HMI display. Let me change my PLC address to its default value. Now click on the CPU and select the General tab. Here we can change the PLC name. Now let's start programming with just this CPU. So under the PLC name, choose the Program Blocks folder and double-click on the OB1 block. As you can see, the working window is changed to an appropriate programming task. This is the program in which we are going to write it. So let me write the program with these instructions. Now which address must be written here? Let me show the PLC wiring. The stop switch is connected to the PLC input with this address I0.2. So I write I0.2 here and then right click and select Rename Tag. Here we write a suitable tag for the address. You can see here that the start switch is connected to I0.0 address, so I can write I0.0 like the previous address. Another way is you can select this address on the CPU, then drag and drop it here. Well, let me change its tag to start. Finally, the K contactor is connected to the PLC output with the Q0.0 address. So I write this address and change its tag to K inside my PLC program. The addresses of this contact must be the same as the output contact, so I can copy and then paste it, or I can write its address or tag. Let me save this project. Now see the right side of the working windows. This is the task window. Now it shows a list of all programming instructions. If you remember, here was the list of modules, while there is the device configuration. The inspector window underneath the working window has three tabs. Firstly, it shows the properties of the object marked. Now it shows OB1 block properties. The next tab is the info tab, which records the sequence of actions, and the last one provides an overview of the diagnostics status of the connected device. Here is the project tree window. The project tree window is displayed with the same content for all editors. Its structure contains all project data and the required editors. If we double-click on any object, its associated editor will be opened in the working window. This is our PLC which has been inserted before. We have worked with the device configuration and program blocks. Next, let me add an HMI device. As you can see, if a device is inserted, the appropriate tools will be shown here under the device. At the bottom here, you can switch between Portal View and Project View. In the middle, you can see the tabs of all opened windows. The far right indicates the current status of project processing. After wiring PLC and configuring and programming in TIA software, the next step is to compile the logic for any error. Click on this icon. TIA will start to compile the project. Well, there isn't any error or warning. Now with this icon, we can transfer this program to the PLC, but which PLC? The real or virtual one? If you have a PLC, Connect it to your computer with a LAN cable. Otherwise, if you have installed PLC Sim software, you can simulate this project. Program downloading in both of them is the same. Let's see how we can have a virtual PLC. Click on the online menu, select simulation and click on Start. This message warns you that starting simulation will disable all other online interfaces. Click on OK. Now you can see your virtual PLC on the left side, which is connected to the TIA software. In this window, click on Search. The TIA tries to find PLCs which are connected to your computer. For me, it found my virtual PLC. Click on Load. Here are some messages. Now click on Load again. Now the downloading is done successfully. Pay attention, there aren't any hardware switches on S7-1200 CPUs to start them manually, unlike S7-300 or S7-400 CPU models. So we need the TIA software to start S7-1200 CPUs of Siemens company. So let's select Start Modules and click on Finish. Now I want to see my program in the PLC, not in the TIA software. So let's click on this icon. When I press this icon, TIA software shows me the PLC program which is connected to TIA. As you can see, the working windows are changed a little. For example, the color of this window is changed to an orange color. The instructions have gone and now a CPU is displayed. Or on the left side, we see some green circles. To test the program, we want to change this normally open contacts to close. If you use a real PLC, you can change it with this switch. But what about my virtual PLC? Or suppose that your switch is broken and you cannot change the PLC input and there isn't any time to repair it. So how can we change the PLC input addresses in these cases? Well, we can do it with TIA software with its watch and force tables. Click on the force table. The first thing you need to do is select any input address in which you want to change it. I select my start tag with the I0.0 address and also the stop tag with the I0.2 address, and here write a valid value. For a binary address like I0.0, we just have two valid values, 0 or 1. In other words, false or true. Let's write 1 here, then click on this icon to use inserted value in the program instead of the real value. Here you can see that the main LED color is changed to orange because this is the way it is usually used in maintenance processes. Also, the letter F is shown here because this contact with an address of PLC input get its value from the force table instead of its input. Also, its color is changed to green from blue and it passes a virtual power to the output. Let me change it again. Now I am going to give 0 value to the start contact. As you can see, here its color has returned to blue and doesn't pass the virtual power. But our output is still on because of this branch. Now I want to change the stop contact. It is expected that the CPU turns the output off. Now let me exit from the simulation and change the program. We use 2 digital inputs and 1 output address in this program. Now let me define the address of the CPU memory. Now I download this program to my virtual PLC again. As you can see, if we want to turn on the output, we need to change this normally open contact with an address on the memory to close, but we cannot do it using the force table for an address on the memory. For contacts that have an address of CPU memory, right-click on that contact and here modify its value to 0 or 1. Now let me show you my equipment and download this program to my PLC. First is the 220 volt AC, which is converted to 24 volt DC by this converter. Then my PLC can be turned on by this switch. Also, these 8 switches are connected to 8 digital inputs respectively. We can understand which input or outputs are activated with these LEDs. See here that I am using this S7-1200 CPU and an analog output module beside that, which is connected to my computer with this LAN cable. The next step is to download this logic into my PLC. Pay close attention. All virtual CPUs must be closed. Otherwise, TIA Portal won't find the connected CPUs. Let me compile this program again for any errors. It shows 0 error and 0 warning, so it is compiled successfully. To download the program, I have to use this icon again. Download to device. But for this test, we are using a real PLC instead of the TIA simulator. In this window, select connection type and then click on Start Search. It will search the IP address which is connected to my LAN card. Well, it found the PLC. Here I can see the connected CPU model. Now I can load my program. This message says, do you want to override the main block? Click on Yes to load the new program. Click on this icon to activate program monitoring. First, let's change this contact with the first switch, which is connected to the I0.0 address of the PLC digital input. As you may know, for a bit of memory, I can right-click and then select to modify it to either 1 or 0. Now the PLC output is turned on. If I turn off the first input, my output remains on, and if I enable the second input, my output goes off. Then let's use the force table to change the input image memory address. Next, let me change the start contact state. You can see here the maintenance LED is turned on. This red F letter appears here, and also the maintenance LED on my CPU is on to notify the operator that the CPU is using force table instead of real value. In this lesson, we have had an overview of TIA Portal software, what the portal and project view are, and also we have done a simple project with a TIA simulator and real PLC. In the next video, we are going to learn some points of ladder programming language, and after that, we'll start programming the PLC. Thank you for watching this video.